Okay, yeah. All right, I hope this is recording. Yeah. Anyway, so yeah, feel free to interrupt anytime if you have questions. This is very informal. So what we're doing today is we're talking about this project that during the last, I guess, 1 year or half of that year, I've been working on together with Stefan Friedl, Lars Munser, who is here, and also Yuri, Santos, Rego, who is in the audience as well. And it's about spatial graphs, something about how you can cut spatial graphs into canonical pieces, so to say, and then how you can distinguish spatial graphs with some algorithm, in theory at least. So one thing that I should get out of the way right away is that everything in this talk is piecewise linear. So everything is piecewise linear. Yeah, often abbreviated PL. So whenever I write a map or an embedding or a sphere or whatever, it's always a PL thing. This essentially just means that all the objects I consider are polygons, and the maps are piecewise affine maps, like they are. Yeah. But if you don't want to think about these details, it's not at all going to be crucial. So let's just get to the fun part. So let's begin with the definition, like the most basic definition, which is that of a spatial graph. And so, as you should expect, this is not the color I wanted. It's okay. As you would expect, like a spatial graph, the idea is that you have a graph. You think of an abstract combinatorial thing, but it's embedded in a 3-sphere. So you also remember this topology. And in particular, you can have knots, which you realize, say, as a spatial graph comprised of a vertex and one loop, and you can knot it in a 3-sphere. So somehow spatial graphs contain knots. But so let's make it precise. Oops, this is not the tool I want. So, okay, typically we'll denote spatial graph by gamma, and it's a triple comprised of a 3-sphere, a vertex set, and an edge set. Okay, so what is this curly S? S is the S is an oriented 3-sphere. It's important that it's oriented. It's not clear yet why that is important, but I'll mention it at some point. So V, okay, and maybe I'll just add here that we call this thing the ambient 3-sphere. So what else do we have? We have a vertex set, which is just a finite subset of S. Finite subset. Yeah, and we'll call it the vertex set. And E, well, E is going to be the edge set. So each edge you think of as a subspace of the ambient sphere that looks like an edge should look, which is the following. So E is a finite, finite set of subspaces. Let's say I call each of them lowercase e and S, such that E is either PL homeomorphic, or it's either an arc with so an arc intersecting V precisely at its endpoint. So E cap V is the boundary of E. So this is maybe the thing you first think of when you think of what an edge should be, but we also allow loops, and these are, well, a circle with E intersection V being a single point. And these edges are, we call them loops. Yeah, so down here I have an example of two spatial graphs that I have drawn. The purpose of drawing them like so is that you notice that they are abstractly the same graph, right? The combinatorics of the vertices and edges are the same. There's two vertices connected by an edge, and each of them has a loop. But in the ambient 3 sphere, they look very different. So they are, well, whatever notion of isomorphism we introduce for spatial graphs, these should not be isomorphic. So let's get to it. Let's define what an isomorphism of spatial graphs is. An isomorphism between two spatial graphs, gamma 1, gamma 2, is an orientation preserving homeomorphism between the ambient 3 spheres. So from, let's say, the ambient sphere of the first graph and the ambient sphere of the second graph. Well, and what should it do? Well, taking vertices to vertices, and edges to edges, bijectively. Okay. Yeah, I also have here another example of two spatial graphs. This time it's maybe not as obvious whether or not they should be isomorphic. Like one of them looks all braided and the other one doesn't. Yeah, but maybe this braiding can be undone. And in fact, that's exactly the case. And this has to do with the fact that we're working in a PL setting. For instance, if you were doing smoothly embedded graphs in a smooth 3 sphere, and you always required your isomorphisms to be smooth, in general, you would not be able to freely move the edges around a vertex and somehow untangle this mess. But since we're in the PL setting, we allow such things. So these are two isomorphic spatial graphs. Are there any questions so far? Okay, so.
Hey, Jose, these handcuff graphs on the first page, they become, if you think of them as slightly thickened and handle bodies, they are isotopic, right?
Say it again, sorry?
Like, if you take a tubular neighborhood of this graph on the left page, then they are isotopic, right?
Yes, but we're not doing that, right?
Okay.
And like, there's a way you can see that they are not isotopic, which is because like one of them has a pair of linked edges and the other doesn't. Right, and this, of course, when you take regular neighborhoods, somehow this phenomenon, you can unlink them by dragging one of the vertices to the other place, and yeah, then they become the same as just a wedge of two circles, both of them. But we're not doing that. We're looking at the actual, graphs. But that's a nice remark. Thanks. Is it clear? Okay, I guess it is. So yeah, so now I'm going to tell you what the main theorem of our paper is. It's that there exists an algorithm to test if two spatial graphs two spatial graphs are isomorphic. Okay, and I'll already spoil the main thing we're going to use in order to prove this theorem. This is a result of Matveev. He wrote a very large volume with lots of results in computational three-dimensional topology, and this is one of the main results in that book. We call it Matveev's recognition theorem. It says that there is an algorithm to test if two Haken manifolds with boundary pattern are homeomorphic. And I guess you don't have to be too perceptive to realize that these theorems look similar. So our result is for spatial graphs, and Matveev tells us something about these Haken manifolds with boundary pattern, whatever this is. So of course, the spirit of our main idea is going to be along the lines of translating a spatial graph into one of these objects and then compare them using Matveev's theorem. So let's see what this means. What is a manifold with boundary pattern? So manifold with boundary pattern is a pair M, and I'll draw the second factor in this pair in red, so MP, where M is a three manifold, or maybe a compact three manifold, and P is one subcomplex of the boundary of M. And this thing is the pattern. So essentially, the idea is that you have a three manifold with boundary. Well, it doesn't have to have boundary, but for us, the interesting case is when it does. You have a three manifold, and you go to its boundary, and somehow you vandalize it a bit. You draw some one-dimensional thing, like a polygon. Yeah, it's just a one-dimensional PL complex, something like this. Yeah, this is what a boundary pattern is. Okay. And for now, so you see that I also have this little word Haken here. So let's maybe for now, ignore this word. Haken. Let's pretend we didn't notice. And and see what the main idea of our result is. Well, I've already spoiled it. It's you want to translate a spatial graph into something of this type, into a manifold with boundary pattern. So the idea is to encode spatial graphs as three manifolds. Well, I didn't use the three, so as manifolds, I guess. As manifolds with boundary pattern pattern. Then use matviv. And somehow the pictures that I have here already suggest how we are going to go about doing this. And it's not a, I mean, it's a somewhat straightforward idea. So you see your spatial graph, you take a regular neighborhood, but then you mark the boundary with these red curves that allow you to reconstruct the structure of the graph. Like, yeah, whenever an edge joins like the region corresponding to a vertex, you put a little circle like so. And then, like, if you have the thing on the right, you can reconstruct the graph because you just put a vertex at the center of these vertex regions and an edge going through these tubes. And this is almost good. So what's the problem with this construction? Well, there's like a few details, but we have to think about them. Still need to, well, one of them is that, in fact, this construction doesn't really distinguish between vertices and edges all that well, because it doesn't distinguish an edge between a two-valent vertex. They look the same, at least locally, right? So for instance, let's say that I add another vertex to gamma here, which results in having another two bits of the marking here on this side. Yeah, and so it's not immediately clear. Maybe if you think about it for a while, you can figure it out, but it's not immediately clear what regions correspond to vertices and to edges. So yeah, still need to distinguish between so edges from bivalent vertices. Yeah, this is somewhat easy to work around, but a bit of a more serious thing that we should think of is that it's not clear how you recover the orientation of S, right? So here S is the ambient 3-sphere for gamma, and it's oriented, and you want to recover that orientation as well from the thing on the right-hand side. So recover orientation of S. And I'm going to tell you how we get around these two little issues at once. Like, it's a neat little trick. So I zoomed in a bit on what this marked exterior looks like. And so here you see that we're near a vertex. Here another vertex, you have some edges. And what we're going to do is, well, we're going to, maybe I'll just draw an example right away. So I'm coming to this edge and I'm going to put here 1, 2, 3. And what is this doing? So this 1, 2, 3 drawing that I put here, this is orienting me the edge cyclically, and it's also pointing me towards the vertex region. And once I have an orientation of this circle and this somehow normal direction pointing into the vertex region, I have oriented the boundary. And once I have oriented the boundary, I have oriented the whole manifold. So I can recover the orientation of S on this marked exterior. Of course, we want this construction to be independent of any choices. So if I do it to one circle, I'm going to do it to all of them. And so the marking is going to look like this. Yeah. Is this sort of clear, at least in principle? Yeah, please feel free to ask.
You needed to add 3 of these little symbols because just 2 wouldn't be enough to determine the orientation.
Yeah,
Right?
like 2 ordered points on a circle do not orient the circle. You need 3, right? Yeah, so that's the idea. But it's cool that this little trick like solves 2 problems at once, right? Because we make it so it points to the vertex regions, and so then we can directly tell where the vertices and the edges are, and they allow us to recover the orientation of S. So this manifold here, so obtained by looking at a complement of the graph and then putting this pattern on the boundary, this is what we call the marked exterior. So we denote it by X gamma, where X is somehow should suggest exterior. So it's X gamma, P gamma is the marked exterior of gamma. Oops. Okay. Yeah, maybe I should also mention that we also have a little trick in this sort of silly corner case where all vertices are isolated, but it's not worth talking about it now, right? Because you see that you only get this information if there are edges connecting to vertices. So if you only have isolated vertices, you don't get anything, but this is easy to work around. It's not a serious issue. And yeah, and so the point of this construction is that, so it's this proposition, oops, no, please don't do this. So 2 spatial graphs are isomorphic if and only if their marked exteriors are homeomorphic. And I realized that I think I forgot to tell you, but it should be somehow obvious that when I say that the marked exteriors are homeomorphic, I mean there exists a homeomorphism preserving the boundary patterns, right? That's what Matveyev's theorem is about. It tells us that it gives a detection result for manifolds with boundary pattern where this homeomorphism that it detects has to preserve the boundary pattern, right? I think I didn't say it explicitly, I'm sorry. Yes, okay, so for now, like if it were not for this thing that I've refrained from talking about much, which is this Haken adjective, if it were not for that, the result would be done, right? Because we have a spatial graph, we construct this marked exterior, which is a construction that involves no choices. And then you test the graph exterior. Like if you want to compare 2 graphs, you test if their graph exteriors with boundary pattern are homeomorphic. And well, this you can do using Haken, and then you're done. So this could be a much shorter paper if it were not for the word Haken. So let's see what this demands of us. But before I do that, are there any questions? Please don't be shy. So, okay, so let's see what the word Haken here means. So a manifold with boundary pattern. Boundary pattern. MP. Let's draw the P in red for consistency. So it's called Haken. So if it is, and now I'm going to drop 3 other properties. So it's like the Hydra, where you cut one head and 3 heads appear. So it has to be sufficiently large. And I'm going to explain what this means. It has to be irreducible. And it has to be so-called boundary irreducible. Yeah, it has to satisfy these 3 properties. Okay, so let's see what 3 manifolds with boundary pattern we can apply matviv to. So sufficiently large. I don't want to spend too much time on this condition. This essentially means that it has interesting embedded surfaces, whatever interesting means. And the reason I don't want to talk about this is because this is not a serious problem for us. In almost all the cases, we can very easily satisfy this property. And when we don't like it, we're in a degenerate situation that's easy to resolve. So I don't want to focus on this. I'll just say that this requirement is easy to take care of. The interesting ones are the other 2. So being irreducible, so I should say that both the sufficiently large and the irreducible property have nothing to do with the boundary pattern, really. They're just properties of M. Okay, so irreducible is a property of 3 manifolds that says that embedded 2 spheres are trivial in the sense that they bound a ball. Balls. Okay, so yeah, this means that whenever you see an embedded 2 sphere, then one of the sides is a ball. It's easy as that. Boundary irreducible is somewhat analogous, but it takes a bit more care to formulate and to think about, and it depends on the pattern. So it's about, so whereas irreducible was about triviality of spheres, boundary irreducibility is about triviality of properly embedded disks. So what this says is that if a circle in the boundary that is away from P, disjoint from the boundary pattern, bounds a disk in M, then that circle already bounds a disk in the boundary of M. And this disk in the boundary is again clean. It doesn't touch the boundary pattern. So a disk in the boundary pattern away from P. So yeah, this property maybe takes a little more time to parse. So let's look at this example I drew here. I just drew 2 solid tori. On the left, the boundary pattern is empty. And so this is surely not boundary reducible because you have a disk here, which is, yeah, it's a disk that's properly embedded, but doesn't bound the disk in the boundary of the torus. But this thing cannot, yeah, so that's right. So this on the left is not boundary irreducible. Whereas on the right-hand side, of course, you cannot construct any such disk. And indeed, if you try to draw a properly embedded disk, it's not difficult to see that it's always going to already be trivial. So this is boundary irreducible. Yeah, but I just want to make an additional point, is that if I change the one on the left, and I put some marking like so here, another valid, somehow non-trivial disk would now be this one, right? Because this curve here does not bound a clean disk on either side of the boundary. Okay. Are there questions now? Right. Okay, so now what we have to do is think about when our marked graph exteriors satisfy all these properties, because that's when we're going to be able to apply Matveev's theorem. And somehow we begin with a very easy observation, which is that if the marked exterior being reducible is the same as the graph being separable in the sense that I'm about to explain. And by separable, I mean that you can find oops, what happened? Why did my color change? You can find a two-sphere, like this one, that separates one portion of the graph from another. So this is what we call a separating sphere for gamma. Sphere for gamma. And of course, when you construct the exterior, this sphere is going to be non-trivial. So it's also going to be a reducing sphere. For the marked exterior. Okay, so yeah, the reducibility problem, like the second bullet point here in the definition of Haken, is a property that boils down to whether your graph can be split like this, or whether it can be expressed as a disjoint union of spatial graphs. And this disjoint union, we're going to make it into a formal operation on spatial graphs. So let us, yeah, so the idea is that now we define the disjoint union of spatial graphs. And somehow it's almost silly to try and draw it, right? So here I have a graph that I call gamma 1. Here I have a graph that I call gamma 2, just something random that I put together. And the disjoint union is, well, you just put them side by side. And how, yeah, so this collection here would be this graph with like these three pieces is going to be the disjoint union. And how do you formalize this? Well, the way you do this rigorously, which is something that we actually do carefully in the paper, is you choose a 3-ball that contains one of this gamma 1, and you do the same thing for the other one. And then you glue them together along the boundary. And when you glue, of course, you have to make sure that you are orientation reversing, so that in the end you get something oriented. And this is exactly the point where we, in fact, use the orientation of the ambient sphere. If the ambient spheres were not oriented, you couldn't really meaningfully define these operations. That's somehow the crucial point. That's why we always want our graphs to live in oriented spheres. And so, yeah, when you perform this operation, you obtain a third graph, and yeah, the boundary of the two balls that you identified becomes a sphere in there, which, yeah, if both graphs were non-empty, then this this sphere is a separating sphere. Is it clear so far? Are there questions? And somehow what we're doing right now is very trivial. It's almost stupid that I'm wasting your time with this, but there is a good reason for it. It's because this story we're telling that is very easy to understand about disjoint unions and separating spheres will have an analog when we want to study boundary irreducibility. So bear with me, and yeah, think not as much about how this is technically done or whether this is interesting, but rather of the structure of this approach. So what we're doing now is defining what we mean by an elementary piece, so to say, for these decompositions. So spatial graph. Now I'm going to call it lambda because that's the notation I like to use for things that you cannot decompose. Is a piece not this. Yeah. A piece if it satisfies two properties. Yeah, so one of them is whenever you express a lambda as a disjoint union of two spatial graphs, this already implies that one of them is empty. So this one is empty, or gamma 2 is empty. And somehow this condition that I wrote just says that that lambda is non-separable. The second condition is that lambda itself is non-empty. Okay, so this is what I call by a piece, and pieces are the elementary building blocks of spatial graphs for the disjoint union operation. They're somehow the prime elements, if you want to phrase it in these terms. So now we have this proposition that it's hardly something that you're going to write home about. It's absolutely predictable that this should be true, but it's interesting that we think in these terms for what comes next. So the proposition is that every spatial graph gamma is a disjoint union of pieces. And so we write gamma is a disjoint union over a finite set of some lambda I. So this is the first part of the proposition. And the second part is that this decomposition is unique or canonical. So this decomposition is canonical. More explicitly, if gamma 1 is isomorphic to gamma 2, then the pieces of gamma 1 and of gamma 2 are pairwise isomorphic. Okay, and what is the upshot of this somehow excursion into trivial things? What does it tell us? It tells us that testing whether gamma 1 and gamma 2 are isomorphic amounts to decomposing them into pieces. And then looking for bijections of the pieces that that pair them into isomorphic pairs. And testing if those are pairwise isomorphic. And again, so just to make it clear, what advantage, like what did we gain from all of this? The thing is that these pieces, they have reducible exteriors. These have reducible exteriors. So somehow my space management is a bit off. It's reducible exteriors. And so, yeah, like we're one step closer to having a working algorithm, right? Because now we only need to ensure that we have this boundary reducibility requirement met. Is it okay for everyone so far?
I have a question. We also need to know that determining those pieces, this decomposition is algorithmic, right?
That's very true. Yes, I sort of skimmed over it, but it's true.
That's yeah. So
yeah, that's doable. Yeah.
Okay, so for example, if you have a triangulation, given the graph has a triangulation or something like this, then you just iterate.
It's an algorithm.
Try all possible combinations of faces and see whether those spheres decompose. Is that how it works?
It's more complicated than that, right? Because it could be that there exist spheres, but you have to refine your triangulation, right? Maybe your triangulation is too coarse to see the spheres, but this book of Matveev that contains our main theorem, it does also give an algorithm for testing reducibility and for producing reducing spheres, which is in fact what we need, right? We need to find the pieces, and we can do that algorithmically. But this is a very important point.
Okay,
I was somehow skimming over it, but yeah, thanks actually for the question. Yeah, so finding these decompositions is also something that can be done algorithmically. Yes, so, all right. So that's somehow the first part of this, of solving the Haken problem. Now let's get to the interesting bit. And that, well, we have to ask the question, when does a piece gamma have boundary reducible say marked exterior? Yeah. So that's the question. And somehow I'm already suggesting the answer, or yeah, I don't know, the following illustration already suggests what we should be thinking about. So here I drew a graph, a piece, indeed, because this is clearly a piece. And to the right, I drew its marked exterior. Well, and here's a reducing disk for that. I draw a curve here, and look, I go around here, there's a reducing disk. And what this sort of suggests, and it's indeed going to be essentially the answer, is that boundary reducibility corresponds to the existence of these so-called cut vertices. So this vertex here is what we call a cut vertex. And what we mean precisely by a cut vertex. It's a vertex that decomposes the graph into two parts that are glued along one vertex. And of course, we always do this topologically. So formally, this means that there exists a sphere intersecting the graph only at that point, and that sphere has portions of the graph on both of its sides. And such a sphere we call a cut sphere. So, yeah, so, and this is a reducing disk.
What about the graph with 2 vertices and 1 edge?
Exactly. So that's the only exception. Very good.
I see. Okay.
So, yeah, but I'm happy that somehow the audience is faster than me. So the answer to that question is when gamma has a cut vertex, and then I will put it in parentheses, or gamma is a one-edge graph. Why? So what is the deal with this one-edge graph? The thing is that this phenomenon of a reducing disk appearing in the marked exterior can occur at vertices, but also at some edges. So it can occur at vertices or edges, but when it occurs at an edge, you can always push it to one of the 2 endpoints of that edge. But if both of those endpoints have nothing else connecting to them, which is the case exactly when you're dealing with this graph that I mentioned here, well, in that case, then you're not getting a cut vertex, because somehow those vertices are trivial in a way. Yeah, was this clear? I think maybe I was a bit confusing now, but somehow this effect, you can always recognize it on vertices except for this case. And then, yeah, we treat this case separately. It's a special case in our paper, and it's somehow easy to deal with, but indeed you have to you have to treat it separately. And so, okay, so we recognized this property of being boundary reducible in terms of a property of the graph, and we're just going to mirror the program that we did for the reducibility thing. So this suggests defining an operation that is just gluing graphs along a distinguished vertex. Yes, and yeah, so let's do this. So we define the vertex sum of pointed spatial graphs. Somehow this is the complicated thing this time. It's that you have to keep track of the vertices along which you glue. Pointed spatial graphs. Yeah, this is an important point. So maybe let's look at this example. Here I have my graph gamma 1, and I'm considering this point u here, this vertex u, and on gamma 2 I have highlighted here also a vertex v, and I denote the vertex sum of gamma 1 and gamma 2 along these vertices with this notation. So I put a dot between gamma 1 and gamma 2, and then I put some subscripts here that tell me where they're being glued. I should emphasize now that this is a bit tricky to define rigorously. Like you have, so how is this defined formally? You have to enclose this gamma in a ball that touches it only at that vertex, and then you do the same thing for the other. Maybe I'm going to draw it as I did before. Like you have a ball for this one, and another one for this one, touching only at the vertex, and then you need a map sending vertices to vertices, you glue. But showing that this is independent of the choice of these balls and of the choice of maps, this is one of the most technically difficult parts of the paper. because it's a very particular behavior that these balls have to exhibit near this vertex. Yeah. So here, I guess on the right hand side, I can highlight this new vertex here that you get from the identification. So this vertex is, yeah, it's the result of gluing U to V, right? Okay, so what did we do last time at this juncture? Well, we went to look for somehow these simple components, like these, maybe we should like to call them prime elements for this operation. So those that cannot admit non-trivial decompositions and are not themselves trivial. So this is what we're doing now. So we're going to define a block. Before they were called pieces, and now, yeah, we say a piece lambda is called a block, is a block. Let's highlight it. I always do this mistake. So first thing is, if you express it as a vertex sum of two graphs, of two spatial graphs, then this already implies that one of them is the trivial graph for this operation. And what would that be, by the way, if anyone wants to tell me? Oops. So I need to write down something after this. Before it was the empty graph, but for this one, yeah, I guess I'll just go ahead and say it. It's the one-point graph, right? And this property that I just wrote is synonymous to saying that lambda has no cut vertices. And the second property is that lambda itself is not trivial with respect to this operation. So lambda is not isomorphic to a one-point graph. Okay, this is what we call a block. And now the nice thing about these blocks is that, well, if they weren't separable before, they're surely not separable now. They're like they were pieces, and they also have no cut vertices. So they're, let's write this in a different color. They're marked exteriors are Haken. Yes, so what was the program that we followed last time? We said for this disjoint union operation, we wanted to say that there is a canonical decomposition, or a canonical decomposition into these elementary pieces. But you see, now is when things become slightly complicated, because before you could just write a disjoint union like this, and this is just described by giving a set of pieces, and there's no ordering to these pieces, there's no combinatorial information about how they are assembled. But this time we have these vertices to glue along, and we're not always gluing along the same vertex of the same graph. And so somehow this is where we have a bit of complication, but it's also where we all have a bit of fun. So the question is, how to write down iterated vertex sums. And somehow the point is that we must keep track of all vertices from all spatial graphs being attached. Yeah, and the tool we use for this is what we call the tree of spatial graphs. So do this using a tree of spatial graphs. And this is what I'm going to tell you about next, of spatial graphs.
Could you quickly comment on how these vertex sums looks like for, like, if you have a trivalent vertex or a quadrivalent vertex, then I could like distribute edges into the two components of the complement of the sphere. Yeah.
So you have one thing which is a vertex sum, and the vertex sum is well defined, right? You start with two graphs that have nothing to do with one another, and then you assemble them. But your question is about how do you disassemble them, I guess. And the point is that there's many ways of doing it. But in the end, we're going to get to a point, as with the disjoint union, that sure, you can start cutting them however you like, but in the end, the result is always going to be the same. And that's what, it takes a lot of work to prove all of this. But somehow, it's good to do the disjoint union case because that's also present there, right? I could ask, if you want to decompose a graph into pieces, how do you do the combinatorics of that, right? You could, if you have, say, 4 pieces, you could distribute them 3 to one side, 1 to another, or 2 to one side, 2 to another. Like this, but we have a way of dealing with this, and somehow it's it's difficult, mostly because of how obvious it is that it works. But a similar thing happens with the vertex sums. So
okay, yeah, thanks. Yeah.
Right. But yeah, okay. So, but thanks for the question. Of course, like there's a lot of combinatorics involved in making sure that all of these things are well defined and like proving that proposition. And we did that carefully, even though it's all very obvious, the one for the disjoint union. But doing that requires really figuring out what the combinatorics are doing, why it's all the same. In a way, it's about exploring the algebraic properties of these operations on spatial graphs. Yes, and somehow now the thing, again, just to remind you, what we're struggling with is, for the disjoint union, we could just write down a finite collection of pieces and say, take their disjoint union. Implicitly, this is using the fact that that this operation is commutative, that it's associative, like there's things being used. And these same properties, we established them also for the vertex sum or analogs of them. And in the end, there is a way of saying you just do the vertex sum along all these things, but you have to give more information. And this information is what we call a tree of spatial graphs. And that's what we're doing next. So what is a tree of spatial graphs? So in principle, it's just a blueprint for you to assemble a spatial graph out of smaller ones by doing vertex sums along different vertices. So I drew an example of a tree here. This is not a spatial thing. This is just a combinatorial thing. So this, what I drew here is a tree. So tree with vertices in 2 alternating colors. You see, I have the green vertices and I have the blue vertices. And so what is this telling me? So the green vertices, so each green vertex is a spatial graph. Yeah, so these things here, they represent spatial graphs. And so you see that I numbered my green vertices with numbers from 1 to 5, and I have a few spatial graphs that I put down here. And the first one, yeah, so say vertex number 1, I want it to correspond to this graph, so I'm going to call this one gamma 1. Okay. Vertex number 2, if you allow me, I want it to correspond to this graph. Vertex number 3 also corresponds to the graph on the left. There's no reason why you cannot do the same thing twice. Vertex number 4 corresponds to this one, which is also number 5. Okay? Now I'm going to tell you what the edges mean. So each edge is a vertex of the graph at its green end. So for instance, edge A here, the graph at its green end is graph number 1. So I should label one vertex in this graph by the letter A. Is that correct? Like, yeah, it better be. And if you allow me, I'm going to pick this one. Edge B should correspond to a vertex in gamma 2, which is this one. And I want it to, and I want the vertex to be this one here. Edge C corresponds to a vertex in that same graph, and I want the vertex to be this one. Edge D corresponds to a vertex in gamma 3, and I want it to be, in gamma 3, which is the one on the left. Oh, and I want it to be the same one as A. Edge E, I want it to correspond to this vertex of the second graph, so this E. And F and G, so F corresponds to gamma 4, which is this one, and I want the vertex to be this one here. And G corresponds to the same graph somehow, so I want the G to be this one. Yes, okay, so what I presented you so far is the data of what we call a tree of spatial graphs, and from all this data, you should be able to assemble a new spatial graph. But what I haven't commented on yet is what about the blue vertices? And well, blue rhymes with glue. So what this means is that you're going to glue all the vertices that correspond to the edges at a same blue vertex. You see, so for example, this blue vertex here tells you that you want to attach the graph gamma 1 to the graph gamma 2 by gluing vertex A to vertex B, and so forth, and so forth. And when you do this to all the graphs, you obtain what we call the realization of a tree of spatial graphs. So the realization of a tree of spatial graphs. So let's highlight it. Again, I think I'm going to do this mistake yet 10 more times before the talk ends, and it's about to end. Yeah, and I had to refrain from putting the image here beforehand, so I'll just add now. To, like, what is the result in this particular case? It's this graph that I drew here, which is, of course, a spatial graph. So you see what happens. So on the tree, you see that vertex 2 is being attached to all the other graphs. And yeah, I have encoded the combinatorics of how you do it. And yeah, in the end, these blue vertices are going to turn out to correspond to, correspond to vertices of the nth thing. In particular, yeah, they correspond to these 3 vertices. So this is how you specify an iterated disjoint union of graphs. And I'm about to finish the talk, because now we have something that is, I don't know, I think we were happy enough with this to call it a theorem. And it's the statement that every piece is the realization of a unique tree of blocks. And by a tree of blocks, well, what do I mean by a tree of blocks? I mean a tree where all the graphs at the green vertices are blocks. So this is one of the important things. And again, uniqueness is the key point, because yeah, that's what we want. Like if you give me 2 pieces and you ask me, are they isomorphic? What I can now do, and this can be done algorithmically, is, okay, I express both of them as realizations of trees of blocks, and then I compare the blocks to see if they are pairwise isomorphic. And I have to be a bit careful. I need to do a bit more, because I have to check that if I find isomorphisms, that they send the vertices to the correct ones, like respecting the combinatorics that the tree specifies. But we can do this. I don't want to go into the details of how, or maybe I'll do it afterwards. But yeah, we can. This is something that can be done. And so, yeah, and then I reduce to testing to the isomorphism problem for blocks, and those have Haken exteriors. So we're done. So just to finish it off, so let's write the upshot here. It's that this reduces testing whether 2 pieces are isomorphic to testing if they have pairwise isomorphic blocks. And here, of course, yeah, via isos respecting combinatorics. Combinatorics. Yeah, so I'm being a bit vague with the combinatorics, but hopefully you realize that it's not enough that the blocks are isomorphic. You have to ensure that the blocks they also attach correctly and send vertices correctly so that you can reassemble them. But yeah, I don't want to explain how we do this, or maybe we can do it later during the questions. But I'll just say that we encode these combinatorics into the marking, like we soup up our marking, so to say. Encode this in the marking, or in the boundary pattern. It's in the marking. Yeah, and so of course, the point of the blocks is that Matveev applies. And so that's how we have a proof that you can algorithmically distinguish spatial graphs. And I guess this is what I wanted to say. Yeah, thank you for being here. I'm very happy to have spoken to you. Thanks. Yeah, and I'm also very happy to hear any questions you might have. Okay, there's something in chat apparently. Okay, something was funny, but I didn't catch it. Yeah, okay. I don't know. Yeah, do you have any questions or concerns or whatnot? Maybe okay, maybe then I'll stop the recording in case you're shy. Let's see if I can find how to